Thank you for joining us today. My name is Mohammed Al-Batal. I'm in the office of the CTO within Seagate. I'm also lead the future technology for the systems team. So my presentation today is about the scale of data in the future and today, and how we're going to bring efficiency to be able to scale to that level. So the level of scaling is going to become more and more challenging, and I'm trying to find out how to here. The latest IDC data is showing close to 400 zettabytes of data will be created. Not all of it can be stored. And one of the biggest reasons why we can't store this data is efficiency is not there for us to have data centers that are big enough to consume that data or to store it in a fashion that is doable today in current technology. So we definitely need to look at the various segments of the data. You've seen a lot of these marketing slides shown around. Some people focus on the enterprise, some people focus on the consumer. We're focused on everything because, mass storage requires hard drives. And hard drives carry the biggest burden of responsibility to store the mass storage today. And we need to create more efficiency in that storage layer in order for us to absorb more of that data and provide more storage than what we can actually do today. As you can see, HAMR technology, we just announced it and we sampled it, and we're almost done with quals. I think a lot of multiple CSPs. The idea is we are moving in a direction where we can create more capacity, which means within the same drive, which means you're actually improving the watts per the terabyte decline. So you're allowing for more power efficiency within a spindle by increasing its capacity. That also helps the TCO, which helps, again, people buying more storage to store on it. So it's not only one function. It's multiple functions that need to be adjusted, right? So the economy of scale, the CapEx to buy storage is going to continue to get better with a faster slope at growing in capacity per spindle. And that's basically what's keeping the CapEx equation from converging with other technologies of storage. Production at scale is another reason, right? So their ability to scale the amount of data required to absorb that mass storage capability, it's easier, relatively, to scale HDD manufacturing than it is to build more fabs, and the cost of those fabs is growing exponentially as we have multi-layer and capabilities of flash are great, right? But for mass storage, for the needs, for the ability to store this mass storage, we're going to need more and more efficiency in our manufacturing capability. And then the sustainability and the embodied carbon per terabyte. HDDs are more friendly to the environment, believe it or not, based on all the embodied carbon analysis that we've seen. So that basically drives the ability to use less power and to consume less embodied carbon or project more embodied carbon per terabyte. So today, I'm not about to talk about sustainability or the market. I just want to kind of show you why efficiency is so important for hard drive and how we're going to deploy that in the future with multiple innovations that happen to be at the nanoscale level, the mechanics, the media, as well as, there are a lot of system-level virtualization that the manufacturer of the storage devices can actually elevate to a box level instead of just keeping it at the drive level, creating more efficiency tools and innovations and tying them directly to be able to scale the capacity of the device and the subsystem. What I mean by subsystem is this basically the box that houses the drives needs to have more intelligence and virtualization to be able to deploy more efficient storage. So the number one thing we started with at Seagate is the last 20 plus years of investment in HAMR technology enabled us to deploy it with 3 terabyte plus platter technology. It took nanoscale attention to the media first, and then to the head technology with the ability to heat the media that has higher coercivity, that allows us to retain the data even at that nanoscale level of media sizes, media grains. What that basically needed as well is not only to grow the capacity, but also to maintain a certain bandwidth per terabyte. So, bandwidth and IOPS per terabyte. Multi-actuator was a necessity. It's not an option anymore. In the future, as we grow into 4 terabyte platters and 5 terabyte platters and beyond, the growth is coming faster than before, right? I showed that graph initially on the first slide, and it showed that actually we're going to grow at bigger increments. So the software adaptability is going to require us to help it with some increase in bandwidth and IOPS at the drive level. So with that, I'd like to dig in a little deeper on the multi-actuator or the dual actuator releases that we've done so far and we plan to do in the future. As we were talking about, there's kind of a mark in the sand here that basically stated that if we fall below 5 IOPS per terabyte, we start having issues in terms of utilizing all that data that we created. So, we drew that line, we created dual actuator, then that basically put us in a special place within the data center workload distribution. So I'm going to spend some time now just talking about the next stage and why we actually, and how the CSPs and the enterprise guys demanded that we find solutions, not only to add more product, but to also add solutions to an existing problem. So if you look in here initially, the distribution of workloads had some hot zones and cold zones on every layer, TLC layer, QLC layer, and the hard drive was suffering because now, as we grew the capacity, it was harder for the drive to handle the 10 IOPS per terabyte. So there were a lot of things that were done in the industry. Some of it relates to NVMe with regards to the ability to do FTP, ZNS, be able to sequentialize the data and make the data more streamlined for the SSD in order to reduce the drive write per terabyte, drive write per day, as well as introduction of QLC that basically took some of that load with even lower cost and more scalable flash technology. However, when you added so much into the data center with 2 new technologies, the cost equation and the ability to put the CapEx and the OpEx to be able to handle that growth in flash now required us to come in with a different stepping in the ability to go back and bring 10 IOPS per terabyte in a special drive that can be more affordable for that market to balance the TCO. So that whole balancing act continues to happen, and this segment is just about to start, even though we've released it, multiple companies announced it. It's about to start in need because it really needs to help the CapEx issue of increasing that data capacity that moved to the lower end and warmed, Ideally, in a CSP, in a hyperscaler, you want to see warm loads in terms of workloads across the whole workload plethora. So with that, there were some important aspects of how Linux and other environments are going to deal with multi-actuator. In a SAS environment, the solution that was contributed to Linux was the LUN level, the dual level of LUNs, and avoiding having to put too many eggs in one basket. So the distribution and understanding that the file system needs to deal with each LUN as an individual piece, but also realize that it belongs in the same box. So those within SAS were the first to be adopted. And then SATA was another way of showing it through partitions. So we actually, the split of actuators within different partitions and the ability to do that within an LBA range. So each actuator had a separate LBA range and contiguous LBA ranges, and then basically the NC queuing was divided, the 32 queue depth capability was divided across these two actuators. So the solutions were there, and the Linux community adopted them. Now, there are some more difficult aspects of it in the traditional RAID environment. So the traditional RAID guys, they did have some resistance to that, but there are solutions. Like one of the applications that we took were to actually partition each group of LUNs and create a RAID 0 over RAID 5 or RAID 6. So you ended up with RAID 50 or RAID 60 to be able to avoid having them in the same RAID group, in the same pool. So you basically split your drives based on all the LUN zeros together and all LUN ones together, and created RAID 60 or RAID 50 for the enterprise-specific market that still requires this level of RAID structures versus the erasure coding that basically has dispersed RAID solutions. But we can't ignore a segment of the market. As we started, we have enterprise, we have cloud, and we have consumer. So we had to find solutions for every one of those segments. So in summary, the traditional increases in capacity of hard drive that used to be 1 terabyte at a time or 2 terabytes at a time, from 20 to 22 to 24, those days are over. Now the change will be, the initial stage is 3 terabyte per platter, 32, we call it 32 or 30 terabyte plus, that will grow until it reaches the 40 terabyte. But basically that is in a cloud environment with variable capacity growth. They will see it a lot more than the consumer. Whereas in the channel, you'll see the bump from 30 terabyte to 40 terabyte plus to 50 terabyte plus. So the growth will be at bigger chunks, bigger bumps as we go on. The challenges of software will have to be, we're going to talk more about that in my session tomorrow. We're going to talk not only about the current challenges with multi-actuator and stuff, but there will be a need to move into interfaces that will help us even better from a future perspective, like NVMe on a hard drive. So we're going to talk in detail about that in the session tomorrow. And then, the foundational technology growth will require changes, at that level of the data sphere, in this level of growth to be able to adapt. So the next stage of this session, we'll talk about the virtualization and the mass capacity subsystem or system level virtualization efficiency with regards to dealing better with at scaling within the box at box level increments instead of scaling at the device alone. So there are some challenges that we tackle and try to keep those challenges within the subsystem instead of breaking them out into the full data center fabric. And the reason why we do that is there were enough studies done, and we got them from one of our partners in the hyperscale. The systems team within Seagate were able to obtain enough data within the fabric of those data centers that indicated that a lot of the data that's moving within that fabric is not the customer data. A lot of it is, erasure coding, replication, rebuilds, but the segment of actually customer data movement within that data center large storage fabric was closer to 25%. The solution to that congestion and data movement was to really try to keep a lot of the replication or a lot of erasure coding within the box, within the subsystem. So grow the thinking from a single drive to a box of drives, just like a single drive has 20 heads, 20 surfaces, 10 platters. Think about the box level virtualization that you can actually scale the number of drives in there without really exposing a lot of data to the fabric. So what that does within our Core Vault, we call it Core Vault, it's a Seagate trademark, but I think a lot of people can move in that direction. It's not really something unique to Seagate. Ability to bring box level virtualization requires us to think at a multi-level of data protection, multi-level of data partitioning. So one of the experiments that was done about 2 years ago, actually, we took scale-out Ceph storage cluster, and we tried to basically compare a JBOD application with Ceph-level erasure coding alone, and came up with a level of comparison of that to a Core Vault or dual layer erasure coding that has very similar efficiency in terms of the number of erasure overhead. Like they went from a 16+4 Ceph over JBOD, and we went to basically taking 16+2 over 16+2. At the end, the efficiency level was about 80 to 79, about the same, but the level of resiliency and durability went from being 10 nines to 14 nines without really losing any of the durability. You were able to get more reliability and durability. What that did also is reduce the congestion at the fabric level, because all the issues that we were dealing with within the drives stayed within that box. Within the box itself, you can hide that from the rest of the fabric. So at the end of the day, you ended up with a lot more savings in terms of BOM cost, from an efficiency and reduction in the CPU overhead from dealing with some of those issues that it was dealing with, including the level of rebuilds, the level of details that it had to go through. And this is kind of a small pool, right? It's not really a big pool of drives within the box. It's reasonably small, but at a 20 petabyte level, imagine the efficiency growth and at exabyte level scale. So that with that, you can actually get a lot more efficiency. So I will answer questions at the end, but I want to see if you have any questions on this specific slide. If you do, please I'd like to clarify that. So integrated within the box, so you have that intelligence within the box. So you have the dual node in here within a box, cross-connected. So it has its own resiliency level to ensure that you're not going to deal with the failure of a mass petabyte level box, right? Because each box was about a petabyte. So with that, you end up with eliminating the necessity of creating that level of rebuild at the upper level. Well, it all calculates back to what's the probability of that happening. You have 6 nines at every box level. I'm sorry? Well, the box level, the core vault solution is enterprise level 6 nines capable of durability and availability and sustainability. So a lot of these calculations within the erasure coding, and I'm going to show you what's in the box here, it's really dispersed RAID within the box. It's a 16 plus 2 plus 2 with 10% sparing of capacity. Flash drives do that. Hard drives do that in terms of ability to have the ability to recover, right? So you take it and you do it at the level of the box, and you create chunks that are, in our case, we picked gigabyte chunks of stripe sizes, right? So you're striping across gigabyte chunks of the virtual capacity of the whole box across the drive. So you end up with stripes that are not across all the drives. Your stripes are overlapping, but they're not, because you're doing 16 plus 2 across, in this case, it was 53 drives or N drives. In our case, what we picked is 53. The number was 2 pools of 53 within the box. You had 106 drives in a box. So with this solution, you end up with a very interesting phenomena here that tells you that even the box level failure, if you have 53 healthy, in a healthy array, 53 drives are actually active. One drive failure makes degraded stripes. So you have some of the stripe, one of the stripe in the overall box, or the two overlapping stripes will be affected, but they're not critical. They can still have a bad read from a stripe, or another drive failure will take place. And at that point, when your second drive fail, multiple stripes are affected, but even those stripes have an intersect point where it's critical at that point. So in that case, you have 3% of the data that was in the box is critical. That means you can't really, if you have a bad block read from that specific data, you're going to have a hard time reconstructing it. So immediately, all the resources within the box go into rebuilding that 3%. But we rebuild it very fast. So that's because you're not really affecting all the drive sets in that box. Then once you rebuild that 3%, you're back to degraded mode, and you can take a third drive failure. Since then, this was 2 years ago when we first released Core Vault with 16 plus 2 support, 8 plus 2, 16 plus 2, et cetera. We now have plus 3. So you can actually choose to increase your number in nines and increase your reliability of the subsystem level with 16 plus 3 or plus 4. And depending on the level of expectations you have from your system on a number in nines, you can actually create more efficiency, more durability at the box level. Go ahead. Yeah, we have, on Core Vault, we have redundant controllers, active. Oh, sure. So where is the erasure coding and the intelligence happening at the box level? The Core Vault box, again, is nothing unique to Seagate. The industry has other solutions with active controllers what was unique for us was we had an ASIC, Seagate ASIC technology that we created that basically made the calculations and the erasure done in hardware. So a lot of that was a mixture of firmware and hardware that was done in an active form that allowed us to do the erasure coding very efficiently with the minimum amount of power and the maximum amount of performance without non-blocking bandwidth and IOPS. So with that, I think that kind of summarizes one level, one layer of protection that within the subsystem. The other layer is, okay, well, the drive has multiple platters and multiple heads. And do we really need to throw away a drive and go crush it or something every time a head fails? The answer is no. The industry worked together on the reman logical depop within the SCSI community, and they came up with the ability to reduce the capacity and re-advertise a new capacity to the host, right? So if within the box you have a drive that lost only one head, you will lose 5% of the capacity of that drive, but you don't lose the drive. You don't have to go remove the drive because it costs quite a bit of money to send somebody to remove a drive and replace it with a brand new drive in the box. The idea here is, okay, the community got together and came up with what we call offline reman, which means if that capacity is no longer accessible, you can actually re-advertise a new capacity and let the host reformat the drive and redistribute the data across spares. Well, there are other ways to do this. The community should come back together and form what we actually formulated as multiple ways you can actually do online reman without having to reformat the drive. You should be able to advertise the LBA range that you lost or the holes of LBAs that you lost based on the loss of that head. And the intelligent controller should be able to rebuild that seamlessly and rebuild a smaller amount of data instead of rebuild the whole 20 surface worth of data. So those advancements are available within CoreVault, but we would like to see the industry move to a community level work at SNIA level or at others to hopefully come up with a host managed or an online reman of some sort. And that's basically an initiative that our team will try to contribute. So let's talk about some of that, the details behind the head failure and how do you need to have erasure coding at the system level in order to be able to recover a drive failure or a head failure. So a distributed erasure coding to start with can treat every chunk as, in this case, the controllers are aware of where the spare chunks are on the drive. So even the failed drive has spare chunks and has, impacted chunks due to a head failure. Now, again, from a drive manufacturer, we have accumulated enough data to tell us that write head failures are a lot more likely than read head failures. So most cases of failure you're going to see in today's version of the hard drive, not because of mechanical issues, it's just the write head wear or contamination will cause the write head to fail before the reader. So in multiple conditions that we're going to look at, is one of the conditions is where the writer head failed and you have enough spare chunk within the drive. We would like to come up with a standardized way instead of a localized within one vendor to ask the drive to heal itself, right? To start moving some of the content that is readable on the surface but it's not writable into spare chunks within the drive. It will be told what to do, given a list of spare locations, spare LBAs, and asked to copy that data. Again, reducing the traffic within the enclosure, within the sub-fabric that we have within the enclosure. Now, in the case of, oh, you didn't have enough spares within that drive, there are two situations. You can actually have the erasure coding controller either just simply read the data from that drive and write it to spare locations across the whole stripe, or calculate it. In some cases, it is faster to calculate it, depending on how busy the system is. If the system is very busy, trying to read from all the drives and write to all the drives, creates a little more traffic than ability to, instead of doing the erasure or reconstructing the data from erasure code, you can actually read it from the available head. But in the case where both heads were damaged, that's the only way to actually do it is to recreate it from erasure blocks or chunks. So in summary, in order to maintain a better level of efficiency at the data center level, we view a necessity for intelligent, fast rebuild and head failure self-healing in order to reduce the waste and the crushing of drives as well. So the next phase is just to answer, within this virtualization at the box level, we were asked, well, why don't you add data reduction? Well, it is possible to add data reduction on hard drives just like it is on flash. Some myth out there says that hard drives can't deal with data reduction or the data produced from data reduction. And when we dug through it, and we actually worked with Mines University, and we basically, I'll show you the study here, found out that it's actually not the fault of the hard drives. It is the problem with the utilities and the way the utilities were written to be optimized for early SSDs that didn't care about write amplification because they had a lot of OP. So even the early Linux, data reduction tools like VDO was one example. So we took that virtual data optimizer, which provides a VDO sits between the block layer in the Linux stack and the file system, and it shows itself as the block layer to the file system. And what it does, it actually eliminates zeros. I didn't have room, so I took that out. Eliminate zeros from the data. It actually compress and dedupe. And basically, it provides, it showed a lot of the studies that we've seen showed that it is possible to reduce data up to 4 to 1. Compression on average across the whole data set. Again, not specifically video or something, it's across the whole data set, variability in data. It's possible to compress up to 2 to 1 and dedupe up to 2 to 1 on average. So 4 to 1 is significant data reduction potential that requires one premise. The data cannot be encrypted. So, and the data, when it's encrypted, it has 100% entropy. And it's hard to do anything to it, whether you're an SSD or a hard drive, right? So we're gonna really keep that in mind, because most of the on-prem data can afford and allows itself to decrypt the data as it's incoming from the user into the head node, and then the head node can decrypt, compress, dedupe, and then re-encrypt and send to the drives, whether they're SSDs or hard drives. The fact that in flight you can actually decrypt and re-encrypt after you did the data compaction is a unique aspect of on-prem because the cloud, the public cloud guys will not do that. They don't even have the key to the data. The data is coming in from a consumer. The data is always encrypted, so you can't compact it. You cannot do anything to it in reality, whether it's SSD or HDD. But what this study, again, that was done by Patrick Croft and Dr. Andre Berkman at University of Mainz, they started with a standard VDO as it was contributed back then. That was about 2021 during COVID days. They actually found 5 different things they were able to do to streamline the output of VDO. What they discovered is VDO was receiving the data from the user and immediately on a small chunk, on a block, compacting, tiling they call it in some cases, the compression was done as soon as you fill a block, write it. So everything was 4K writes coming out of it, random. Same thing with the dedupe function. It was not trying to coalesce anything, trying to minimize the impact to the memory on the server. So they basically delayed the block allocation. They prevented the need for duplicate checks by providing a better hash that, going from murmur hash to something that gave us 10 to the minus 23 possibility of false duplicates. And then reduce the region between duplicates in terms of LBA range, made some constraints, cached the block and the journal maps, and added read prefetch. The result was a very streamlined output. Now, obviously, this resulted in about 18x improvement in the hard drive performance with sequential write, 86x enhancement of hard drive performance with random writes, and with the sequential random reads, they got a more modest improvement, about 1.5%, 1.5x. What that resulted is, the whole experiment showed that you can actually reduce the data 4-to-1 in on-prem, unencrypted data, and still get 1.5x total performance enhancement of the drive. So 50% enhancement of the performance of HDD with 4-to-1 equivalent compaction capability as SSD. SSDs will benefit maybe more on performance. Maybe they'll get better write amplification. They get more benefits. But this study showed that they both can simply get quite a bit of improvement. They both can benefit from, in an on-prem situation, from data reduction. And it's not destructive to the storage layer of HDD. It actually helps the HDD as well. But in a public cloud, the majority of data stored there is encrypted, so it's not going to have that same benefit. That's all I had today, but again, there's a session tomorrow that I'm going to talk about further improvements with the NVMe HDD proposition that we have. We actually did quite a bit at OCP and other places for it. I hope that we can spend some time on questions, and I can go back and flip to any slide you guys want. Thank you. Sure.
So on your on the slide for the core mode with 16+2 plus 2 very close, how is the block level presented to the operating system? Because you said that the
So what we did here is, so I think how is the block presented in the case of 16+2 at the array level, or as well as at the Ceph layer. So the Ceph was, the Ceph example was all of it 16 plus 4, right? There were no erasure coding at the JBOD level. In our experiment here with Core Vault, we were able to split it into 2 layers of erasure coding, 16 plus 2 within the box across 2 pools of 53 drives, and then 16 plus 2 done at the Ceph layer. What that did is our drives got translated to Ceph as multiple LUNs. So it's a block layer. It's a virtualization. So instead of showing, Ceph, in this case, we actually showed Ceph 8 LUNs per pool. We just picked that number and we tuned it to get the best performance. But in reality, the array can actually chunk it into big LUNs or smaller LUNs.
Yeah, that influences how you create OSDs, right?
Yep.
You manage your fault domains. That's why
Yeah, you kind of shielded your fault domain a little bit.
in a sense, yeah.
Yeah.
I was wondering how, because otherwise you would see just a big block.
No, yeah, you can actually, the controller supports up to 1024 LUNs. So you can actually make smaller LUNs if the application likes them better, or bigger LUNs. The restriction, I think it's 1 LUN per pool, which in this case, it will be 2 LUNs, 2 massive LUNs. It is interesting how also the erasure, when we had we call it ADR, adaptive drive regeneration. The idea of keeping the failure domain smaller was very important for us because, again, number one, you can actually start allowing self-healing to help improve your reliability and reduce the waste, because a lot of the rare earth material that is used on hard drives, when you crush it, you can salvage a portion of it, but not all of it. And that would be a really disastrous if we have to eventually store hundreds of zettabytes of data. Yeah. So it really, the economy of dual actuator, single actuator versus dual actuator. A dual actuator, I'm sorry? Compared to multi-actuator. So we started with a single actuator solution and we optimized that for the last, 50 years or so. And dual actuator presents an economic challenge, right? So people looked at it and said, oh, it's more expensive. Well, yeah, it is, but it's a necessity to reduce your OpEx. If you want to, increase capacity and increase bandwidth, there's a price to pay. Can we reduce that further? I think with economy of scale, as our manufacturing, our printing machine basically uses a single SKU and we unify around dual actuator, that becomes cheaper and cheaper to make those. But it's not going to be at the same cost of a single actuator. Now, with multi-actuator, the complexity grows. If we have to go to 3 actuators or 4 actuators, complexity will grow. Do we need to yet? We'll have to keep asking the hyperscalers and the community, when do we really need to go to the next level? There's a threshold where it will force us to go there. Maybe we can find better ways of designing a reader capabilities or the channel model where we can actually do more streamlining. Maybe through the interface of, if we go to another interface, which I'm going to talk about tomorrow, NVMe flexible data placement. Maybe you can have more flexibility, more drive-suitable placement of data based on the serpentine of data. I don't know if you know, we write the LBAs in a serpent across platters. So we basically could find ways to facilitate more efficiency and more performance out of a drive without having to add a third actuator, or before we have to add the third actuator. Eventually, we're going to have to increase that capacity, that performance that way too. Go ahead. We're at this point, I think we started early. We started early because we had a necessity and request by the consumers, right? Eventually, we realized that the demand was not as strong yet because apparently the software guys found another way of dealing with redistribution of workload. As I was showing you, they added QLC. They did quite a bit of reshuffling of the workload. Eventually, they're running what we're being told is at 3 to 4, maybe right at, depending on the answer you get, is between 3 terabyte per platter and 5 terabyte platter. We're going to definitely need to go to dual actuator in more volume. That's the expectation. Go ahead. So the question is, if you have a single head failure, do we have any statistical data on the next drive head failure? We've done some of this study in simulations. We do a lot of simulations on the drive, on the failure scenarios, and the data that we get from the field. There's nothing that says that a single head failure due to contamination or due to wear doesn't, just like the light bulb problem, they're really independent, with the exception of a drastic contamination situation where you have a head crash or something that really, but that's a small amount of probability, right? So the smaller probability is to have a contamination that affects a lot of head. But normally you have a single head failure, you could have a second one within a period of time that's the probability is about the same as the first head, even having the failure in the first place. So the probability of the first head failure and the second head failures in most cases are independent. And that basically tells us, especially in an online reman situation, we should be able to support 1 head failure, 2 head failure, 3 head failures. It depends on what your tolerance is in terms of performance. How much performance buffer do you have? And how much spare did you put within your pools, right? And those becomes a choice of the developer, right? If they want to create a box that lives for 5 years untouched, or 7 years, or whatever, you can actually tune it by putting the number of drive spares that you allocate, capacity spares, as well as how many head failure per drive do you allow before you actually send somebody to replace it. Go ahead. Well, the detection is definitely by the application that we have within the current box. In the case of a client who's still insisting on using JBODs, they have to realize that this drive has bad LBAs from a range of LBAs that expects to be on the same surface. And the reporting back to the host with drive telemetry can actually tell the host, okay, we have, you have an issue with that surface. Then you can actually start issuing rebuild at the host level or within the array level. You wouldn't know. Yeah, I think it's a good question. I think the drive itself will do self-check. Yeah. But again, I'm a systems guy. I'm always told that the drive is filled. Well, I think that's all the time we had. Thank you very much.